Bueno, pues muy buenas tardes. Es un placer introducir hoy a nuestro conferenciante, que es el profesor Gerard at Hooft, pero los españoles solemos decir Gerard Hooft, que nos va a hablar del LHC, el Gran Colisionador de Hadrones. Sobre el bosón de Higgs en particular va a discutir mucho y decirnos en qué punto nos encontramos de esta búsqueda apasionante. Me han pedido que haga una muy breve introducción del profesor Hooft, así que daré un par de pinceladas. Bueno, es un físico holandés, es un gran físico, uno de los grandes físicos vivos, y ya le viene de familia porque un tío de su madre ya tuvo el premio Nobel, es Fritz Zernike. Incluso tiene un tío que es un profesor muy conocido en física teórica, que era el profesor Van Kampen en la Universidad de Utrecht. De hecho, él ha estado casi toda su vida en la Universidad de Utrecht, donde ha hecho el doctorado, y ha hecho su carrera, excepto, bueno, ha ido al CERN como fellow un par de años, y luego ha estado alguna estancia larga en Harvard y en Stanford, pero básicamente toda su labor ha sido en Utrecht. Realizó la tesis con Tini Bellman. Y esta tesis ya es algo impresionante, es lo que fue sobre la renormalización de las teorías Gauge, sin masa y con masa, y demostró que eran renormalizables. Y esto fue una cosa importantísima. Mirar, se conocía el modelo se habían propuesto ya las simetrías del modelo estándar de la física de partículas en trabajos de Schwinger, Glashow, Weinberg y Salam, pero no se sabía calcular. Cada vez que se calculaba el nivel cuántico salían infinitos, aquello no tenía sentido. Entonces, como trabajo de tesis, muy joven, lo que hizo Gerard at Hooft es demostrar que si se metía el bosón de Higgs, todo se volvía consistente y se podía predecir, se podía calcular, las probabilidades tenían sentido, digamos, limitadas al 100%. Y bueno, pues, o sea, que era la renormalización de lo que se llama el modelo estándar, o sea, que le dio esta consistencia, bueno, que es algo fantástico. Y por esto le dieron el premio Nobel en 1999. Pero a nosotros los físicos nos ha influenciado en muchísimas otras cosas. Por ejemplo, ya en la tesis doctoral, en el periodo después, voy a señalar solo un par de cosas, porque se trata de oírlo a él. Pero, por ejemplo, la demostración de que en las teorías de interacciones fuertes, lo que te explica por qué los quarks están en protones y neutrones en los núcleos, por qué son asintóticamente libres. Y esto quiere decir una cosa extraña, que es que la interacción cuando vas a más cortas distancias se vuelve más débil, es libre en las partículas, y en cambio no lo puedes, se vuelve más fuerte a largas distancias. Y es una propiedad de las interacciones fuertes de QCD. Y él encontró la fórmula y no la publicó, pero la encontró y la contó, y poco después la reencontraron y aplicaron otras personas por las que tuvieron el premio Nobel, que son Wilczek, Gross y Politzer. Bueno, yo creo que desde los años 70 sus ideas nos han dirigido a todos los físicos o nos han impactado en muchos temas, uno sobre N. Hay algunos trabajos preciosos, por ejemplo, esto lo va a entender todo el mundo, que en las teorías más allá del modelo estándar, pues se predice que puede haber cargas magnéticas, monopolos magnéticos. O sea, igual que hay el electrón con solo carga eléctrica, que hubiera partículas con solo carga magnética o entidades con solo carga magnética. También en el confinamiento, en fin, muchas cosas. Y últimamente sus trabajos son más sobre efectos cuánticos en la gravedad, agujeros negros y sobre los fundamentos de la mecánica cuántica, que está trabajando intensamente. Ya acabo con esto, para dar un toque un poco más personal o anecdótico. Yo creo que muchos de nosotros, por supuesto los físicos, estamos impresionados pues, por esta consistencia y esta claridad que ha dado a muchas cosas. Y cuando oímos una charla o su física, pues es impresionante, bien. Pero digamos, yo recuerdo, por ejemplo, tengo una fuerte impresión de hace años ya, una de las veces que vino a Madrid, porque él viene a menudo a Madrid, en particular a la Universidad Autónoma, ha venido varias veces, y todavía hace unos meses estuvo en un coloquio. Bueno, pues viene de vez en cuando, y recuerdo una vez sentados varios, tomando un café en la Plaza de Oriente, en el Café de Oriente, ¿no? Y se puso a explicar muy sencillamente cómo funcionaban los diques de Ámsterdam y de los Países Bajos. ¿vale? Porque su padre es un ingeniero marítimo y, bueno, pues él entendía mucho de esto. Entonces, sencillamente nos estaba contando cómo funcionaban, los problemas que había habido, los proyectos futuros, etcétera, ¿no? Y era impresionante para mí, veías una mente cristalina y absolutamente precisa, era fascinante oírle en una cosa de la vida de todos los días, ¿no? Y bueno, pues yo creo que con esto acabo y estamos aquí para oírle y bueno, pues le doy la palabra al profesor Hooft o at Hooft sobre la física del LHC. Por favor, Gerard, go ahead.
Thank you very much, Professor Gavela, for your very kind words. And now I will explain to you. Of course, I'm very happy to have been invited at this place to talk to all of you. I'll try to say in plain English, unfortunately in English, but I have to say it in English as clearly as possible, what is happening in our field of the subatomic particles. Until shortly, the lead in this kind of research was always taken by the United States of America, where the most powerful particle accelerators stood that actually act as a microscope. Today, we can be proud of having the biggest microscope in Europe, a microscope with which one can look at smaller structures in space-time than whatever has been possible before. So if you would be flying in an airplane high above the frontier between France and Switzerland, you might be flying above Geneva, let me see, yes. Here is the border between France and Switzerland. Here is Lake Geneva. Out there, a little white spot, I can't see it so clear from here. There is a famous jet d'eau, the fountain in the Lake of Geneva. The Alps are on the background, the Mont Blanc is somewhere here. On the foreground, what you unfortunately do not see is this red circle. The reason why you don't see it is that it is a tunnel underground. At some places, 100 meters deep, sometimes less deep, but it is a practically circular tunnel with a circumference of over 26 kilometers. What you definitely do not see when you're in an airplane is that inside the tunnel there are bunches of particles going in opposite directions, actually much faster than I can display in this picture. These particles are made to collide at various spots indicated by little circles here. And at these spots where the particles are collide, physicists are studying what is happening when they collide. They collide with the highest possible attainable energy. And the rule in physics is the higher the energy with which particles collide, the smaller the physical structures are that are actually relevant for what happens. So this is why effectively this machine acts as a microscope. It tells us what happens at the tiniest imaginable distance scales. The machine, which has been inside a tunnel for a long time, for over 10 years, was called Large Electron-Positron Collider. It is a machine in which electrons collide against their own antiparticles in a very similar way, going in both directions. Electrons go one way, the positrons went in the other way, and they were made to collide. Now, electrons are very light particles. It is difficult to give them the highest possible energy. Now, the machine has been replaced by another machine which doesn't have electrons that collide, but protons and heavier particles. And that's why it is now called Large Hadron Collider. Hadron stands for strongly interacting particles such as the proton. But the other particle that's being collided is the nucleus of lead. Lead is one of the heaviest elements available. Lead nuclei are also sent around in the circles in both directions, and physicists are eager to know what happens when these heavy particles collide head-on. And I'll explain a little bit later about the details of that. So that is called a Large Hadron Collider. And that is a machine which is there now and which now acts as our microscope. Inside a tunnel, the situation looks like this. Actually, this picture was made by a Taylor lens, and that is why you can see that the tunnel is curved. It is a circular tunnel with a circumference of 26 kilometers. These blue big cylinders that you see here are actually magnets. They are the most powerful magnets that people can make with such large dimensions. Each of these magnets is 15 meters long and has a weight of 35 tons. This is the main type of magnet. There are other magnets which are needed not only to steer the particles around in a circle, but also to control the beam of particles. So the whole thing is filled with magnets. These magnets are cooled to very low temperatures, 1.9 degrees Kelvin above absolute zero. That is needed for two reasons. One is you want to have very high electric currents in these magnets, so high that they generate very strong magnetic fields, and strong electric currents are best produced by sending them through superconducting material, and several kinds of metals become superconducting at very low temperatures. The other reason why you want low temperatures is that way you can make a much better vacuum. The particles are inside the magnets, they're going in tubes, and you want to have a very high vacuum inside such tubes. Otherwise, residual air particles would slow these things down. Let me now for quite a while elaborate on the theoretical situation, our understanding of the fundamental particles. And for that I go back for a short instance to 1969. I choose that date because that was the time when I was a student of theoretical physics at Utrecht University, and at that time I was learning what was known about the subatomic particles in those days. And what was known is that there are various kinds of particles, and when we talk about particles, we do the same thing as what biologists do when they talk about species of plants and animals. You group them into families and genera and species and so on. We do the same thing for particles. So there are families of particles called leptons, hadrons, and the like. You don't have to remember all these details. This is just to indicate that, like biologists, we put particles in groups and families. We give them names. The names we give to particles are typically Greek letters or Roman letters, as the case may be. And the little numbers at the right say that some of these particles are electrically charged and some of them are electrically neutral, like the zeros. You see the different kinds called mesons and baryons. They are the so-called hadrons, and the counterparts of the hadrons are the leptons, which are the electron and the muon. The muon is a heavy particle that in other respects looks very much like the electron. And there are neutrinos, neutrinos of the electron type and neutrinos of a muon type. And we learned that these particles have a lot to do with each other, so we draw a box around them. The photon is a particle that is associated to all the electromagnetic phenomena, in particular with light. Photos is the Greek word for light, and this is the photon is a particle that carries light, but also carries along the electromagnetic force. Some of these particles also are associated with antiparticles, so the list is only complete if I also add the antiparticles. Not all of them are antiparticles. These creatures, the mesons, are equal to their own antiparticles, so pi plus is the antiparticle of pi minus. I don't have to mention them separately. But all these particles have antiparticles as well, but they look exactly the same, except that everything is sort of opposite. So I don't have to mention them in as much detail as the particles. This was very much the state of affairs around 1969. On top of that, we knew that these particles are subject to forces. And if you want to understand the dynamical properties of the particles, you have to understand the forces that act on them. And what was understood is there are 4 types of forces. The electromagnetic force, having everything to do with electric charge and with magnetic properties of particles. There was the so-called strong force and weak force. These are other kinds of forces that act deep inside the atomic nucleus. And then there's gravity as a very strange residual force that acts all around us, but is far too weak to be directly observable when you look at the ways particles interact among themselves. Then gravity is a very weak force. Now, about the strong and the weak force themselves, we knew very little. For instance, we did not know whether there exists only one strong force or maybe very many of them, whether there's only one kind of weak force or many types of weak force. We did not know that, but this was a subject of study. Now let me begin with the weak force, because it was very soon realized that there was something very special. And you can try to understand all the things that happen when there's a weak force. A weak force would usually cause a transition of particles into other particles. So here you see an electron colliding against a particle called U. This is the name of a constituent of the nucleon particles called quarks. U stands for the up quark, D stands for down quark. What can happen with a weak interaction is that the electron can transform into an electron type neutrino. The U can at the same time transform into a D. This is a kind of weak interaction that can happen. Why this happens was not understood, but we knew there was something of this sort taking place because these interactions are being observed experimentally. Now, a similar weak interaction occurs if you replace the electron by a muon and the neutrino here by a mu-type neutrino. But you leave these things the same. Conversely, you could replace them by another type of quark. This would also be a weak interaction, which would be observable because these quarks would come out in a different state than would have been possible otherwise. So this was a weak interaction that could be observed. And you could also make substitutions in these other 2 lines. So these are the weak interactions that were studied. Now the fact that I can make a substitution with these 2, and I can make a substitution here, suggested that the weak force takes place in 2 steps, so that you really have to regard the weak force as a 2-step process, that something happens here and something happens very close by here. The 2-step process could be understood as a process where temporarily a new particle is being produced called W. W stands for weak force. It is the particle that generates the weak force between particles here and particles here. So this explains why you can make, if you have different particles coming in here, it would transmute into a different particle, or some transmutation would take place at this spot. But then you had to understand that there had to be a particle exchanged. we work out and study the observations very carefully. It was determined that this particle would have to have spin. It would be spinning around. Spin is very much like spin in a tennis ball or a football. Particles rotate around when they move. And so do these particles here. Many of the particles that we study have the property that they're also rotating. And the rotation of this particle was established by saying it has spin of 1 unit. Many of these particles have spin of only 1/2 of a unit. This is what we understood, but otherwise there were still many mysteries. Now, when people studied the various transitions that can take place, the electron can transmute into an electron type neutrino or otherwise. The mu neutrino could transmute into a muon or the other way around. Protons could go into neutrons, or protons could go into a lambda particle, a different kind of particle. Now, when you study the strength of these interactions, you find something quite remarkable, which was understood in the days when I was a student. At least it was known, but not quite understood. And there was quite a slight mystery when you study these things in detail. You find there was a slight mismatch between the transitions here and transitions here. The electron and the muon go exactly with the same weak force, but these transitions were slightly weaker. But then one day, when people were working at CERN, my advisor, Martinez Veldman, was working at CERN, and another person there was Nicola Cabibbo, an Italian physicist, who was also working there. And one day, Veldman recalls, Cabibbo came rushing in his office, and he said, "I found something, I discovered something." He shouted, "Tini, it is an angle." What did he mean by that? Well, you have to look at the things the following way. The electron going into an electron neutrino or a muon going into a mu neutrino, you can say that that is a transition in a certain direction in some internal space. Then he said, well, the same transition for the proton going into a neutron or a proton going to a lambda, that is one transition. It's not two, but it is, you have to display it as a vector, which is slightly rotated. And when you rotate the vector, you find that if you project the vector along the axis here, then you get a length which is slightly reduced. If you project it here, you get a length which is quite considerably reduced. Now, you have here the cosine of the angle and here the sine of the angle. The strength of the force is obtained by taking the square of these expressions. So he found that if you say that this cosine is 0.95, and this is 0.5, then you say 95% of the interactions go in this direction, 5% go in that direction. Since this is 95, it means it's 95%. This force is slightly weaker than this one, and this force is considerably weaker, is only 5% of that. So when you realize that that's the situation, you find that also this transition has exactly the same strength as there. And this important observation turns the weak force into a universal force. So Veldman was very impressed by this observation by his friend Cabibbo, that he said, I'm going to figure out how the weak force works. So he realized that the weak force must be as fundamental as electromagnetism. So electromagnetism can be thought of as being transmitted by the photon. The strength of the forces that two particles exert on each other is dictated by the electric charge. Now, all fundamental particles have the same unit of electric charge, typically the same unit as a single electron. Sometimes twice that, but usually they are singly charged, or they're neutral and then they don't participate in the interaction at all. But all charges of particles are equal. Now Veldman realized that the same must be true for the weak force. These charges have these objects have some sort of weak charge, but the weak charge does cause a transition of a particle into another particle, here and here. But the strength at which they do this is universal. So the weak force is a universal force. It should be as fundamental as electromagnetism. That was his conviction, and he tried to work it out. Now, already something like 10 years earlier, there had been a new theory devised by Young and Mills. Young already was quite famous for other discoveries he had made in physics. Mills was his collaborator at that time, and together they worked out new kinds of field equations. They imagined a new kind of force to exist in nature that resembles very much electricity and magnetism, but it is different. Imagine something like an electric field sitting in some region, and imagine a particle going through that field. Normally, a particle would be deflected. It would feel the force of the field. But Young and Mills discovered that you can generalize this idea in such a way that if a particle goes through that field, it transmutes. It makes a transition to another particle. And if you take that particle and you send it back, it will again transmute and turn into a proton. So protons and neutrons could make transitions by going through this field. This is called a Young-Mills field. It is different from electromagnetism because in electricity itself you don't get such transitions. The equations that they wrote down for this are more complicated than the famous Maxwell equations that describe electricity and magnetism. But they could write down the equations and that way generate a beautiful theory. So you can of course ask, or before going back, you can ask what happened with electric charge. The neutrons were electrically neutral, but the protons were electrically charged. So how did they get the electric charge when they went through the field? The answer is that Young-Mills fields also have energy quanta, just as the electromagnetic field has, but the photons of Young and Mills themselves may also carry electric charge. So that's how, if a proton goes into a neutron, the electric charge is carried away by the Young-Mills photons. So Veltman realized that what we are dealing with here is a theory where photons themselves carry electric charge. As a consequence, photons can interact with themselves now. A charged photon can interact with another charged photon by exchanging a neutral photon this way. Now, this was a new feature of the Young-Mills theory that does not occur in the old electromagnetic forces where the photon can only be exchanged between other particles, but it itself doesn't carry electric charge. So this was a theory that had to be worked out. However, something was very badly wrong with this idea. What is wrong? Actually, there's two things, if you think very carefully. One is the range of the force. Electric and magnetic forces carry very far. In fact, in the galaxy, one can sometimes identify magnetic fields that run all the way from one star to another star. So magnetic fields have gigantic range. Electric fields also, they go far distances. And as a consequence, all the signals that you send using electromagnetism go with the same speed, the speed of light. Ordinary light is an electromagnetic phenomenon, but also radio waves are electric or magnetic in nature. They all go with the same velocity. And that has everything to do with the fact that the field that is associated with that has an infinite range. Now, when you compare that with the weak field must somehow be a field with a very small range. It doesn't carry very far. The weak boson only transmits its force if the 2 points are very close together. That is why in the old experiments, it seemed as if the weak force takes place at one spot entirely, only at one spot, because the force it carries only for very small distances. So only when two particles come very close together, they feel the weak force. And that is where the weak force is fundamentally different from electromagnetism. And whereas the Young-Mills theory did not contain that, it would postulate that also this force would carry very far. Now, the range of a force has everything to do with the mass of the particle. The more heavy a particle is, the shorter is the range of the force. Now, the weight of the particle has everything to do with the energy needed to create it. The higher the energy is that you need to create the particle, the smaller the range of the force that it transmits. This is also why very high energy corresponds to looking at very small distance scales. And this is one reason why LHC generates so much energy in the particles, because we want to see what happens at very tiny distances. So now, Veldman, but also before him Feynman, realized that therefore you had to modify the equations that Young and Mills wrote down. So what can you do? Well, how do you modify an equation to have it behave the way you want? Well, you try it a bit, you discover you have to do the same thing as other particles with mass. You have to add a mass term to the equations. Now, I will not bore you with the details about how to do that, because that is very technical mathematics. But it seemed as if by one slight modification of the equations, you could accomplish two things. You could accomplish that the force only ranges at very small distances, and at the same time, you could accomplish that the particle responsible for the force is a very heavy particle. And so they did that, and they sat down and did calculations and asked what happens. So they started to compute all possible transitions that can take place. In the simplest case, a particle is simply exchanged from one spot to the next. But the nature's laws then demand that if this can happen, then this can also happen. The particle can be exchanged, but associated with that exchange, another exchange takes place. So what happens if more than one exchange takes place at the same time? This was needed for consistency of the theory. If you don't assume that, you can prove that the theory cannot give correct predictions. So these effects had to be calculated, and this was where the difficult problems arose. It did not quite work, except if you consider one additional exchange. So Veldman and Feynman and others computed these diagrams where either the particle that is subject to the Young-Mills force is created in pairs and annihilated again, or the Young-Mills particle itself exchanges something with itself. This is a self-interaction that can take place. These are the simplest examples of self-interactions that can take place. There are many more complicated ones, but Feynman and Veldman discovered that as long as you keep only one thing going around in circles, one loop, then everything is fine with this theory. So Veldman thought, I am halfway solving the weak interaction. If I can also show that the more complicated transitions also work out fine, then I have a beautiful theory for the weak force. He worked very hard at this, but ran into difficulties. This is one page of a long and complicated article that he wrote, and only very few people could understand what he was doing, because he was trying to compute what happens when you have multiple diagrams, and he found that the whole problem exploded. He could not get the equations to work. Something very badly was wrong here. So it was wrong as soon as you had multiple exchanges of this sort. And then it was discovered, and this was part of my thesis work, and this turned out to be very important, was that you need an extra particle to make the theory consistent again. And there's an extra particle which doesn't spin at all, it has spin 0, and it was later to be called the Higgs particle. So why did we need this extra particle? Well, there was something that had been overlooked at this point. And actually there are two things that have been overlooked. One thing is that, as I said, a particle can spin, but particles like the photon, which always go with the speed of light and transmit forces with infinite range, such particles can only spin in two ways. A particle that is massive, for instance the particle that you get if you add a mass term to the equations, that particle can spin in three different ways. Why this is so is difficult mathematics, and I cannot explain it here to you. You would have to follow a lecture course at our university, a graduate lecture course, so it will take some time. So just take now for granted that this is true. A particle with a short-range force can spin in three ways. The long-range particle can only spin in two ways. So one spinning mode of the particle was simply missing. And, but there's something else as well, that there was a breakdown of symmetry. The Yang-Mills theory causes a transition between one particle and the other particle, but that only works if the two particles are exactly alike. And again, I like to compare particles with vectors, with things that have a length and an orientation. The electron can be represented by a vector in one direction, the electron neutrino a vector in the other direction. And the Yang-Mills force causes a transition between electron and neutrino. But according to the original Yang-Mills theory, that only works if these particles are basically identical to each other. There's no observable distinction. Well, that cannot be exactly right. The neutrino is certainly different from the electron. The electron has a mass. It's not very heavy, but it has mass. The neutrino, as far as we knew in those days, was massless. Today we know also neutrinos have a mass, but much, much lighter than the electron. But anyway, neutrinos are different. They are electrically neutral. The electron is, of course, electrically charged. So there are very deep and important differences. Yet, the Yang-Mills theory can cause transitions between those. However, the equations then fail to produce sensible physics. So here also, there was something very fundamentally incorrect. We now say in modern terminology there is a symmetry. There ought to be an exact symmetry here, but the symmetry is broken. And how can that be? Well, to break the symmetry, there's two ways. You can break it by brute force, by ignoring it, by writing down equations that don't have that symmetry. That turned out to be wrong. That does not give a consistent theory. Now, the consistent theory already had been proposed quite a few years earlier by a person named Peter Higgs. But it would only be fair to add to that two other people who observed the same thing a few months earlier, François Englert and Robert Brout, who worked together in Brussels on the same ideas. They all realized that the symmetry has to be spontaneously broken, not explicitly broken. Let me try to explain to you what spontaneous symmetry breaking is. It was beautifully explained when, a few years ago, Nambu, a Japanese physicist who is now quite of age, received the Nobel Prize. He considered himself too old to give his Nobel speech, and so he invited a younger collaborator of his, the Polish name Bialniczy Birola. He invited Bialniczy Birola to give the talk for him. And when I saw the talk on the web page, I liked very much his way of explaining spontaneous symmetry breaking. He said, imagine a pole. It could be a pencil or a pillar or something of some material, and suppose that you pressure it down. You put a pressure on top of this pillar. In the first approximation, the pillar will just become a little bit shorter. If you press very hard, it becomes a bit shorter than the pillar on which you do not press. But if you press too hard, it will start to buckle or to deform. So now you can ask, in which direction will it buckle? In which direction will it deform? To the left or to the right or other directions? It is unpredictable. It will buckle one way or the other, but you can't predict in which direction. It doesn't matter. the equations do not tell you how it will buckle, but they will tell you it will buckle in one particular direction. This we call symmetry breaking. The fact that this pole here by itself chooses some direction to bend in, that it chooses a way to break the symmetry, but we can't predict how. That we call spontaneous symmetry breaking. A different way to illustrate the same phenomenon is to consider a particle that could live on top of a Mexican hat. This is, well, we call it, scientifically we call this a potential, a energy potential, but you could use the word Mexican hat. It has a perfect rotational symmetry. So you could now put a particle on top of the hat and ask, will it stay there? Well, it might, but odds are that it will fall in a more stable position in the rim of the Mexican hat. Once the particle sits in the rim, it can rotate around, which otherwise it could not. So now the particle can run around in the rim of the Mexican hat. That gives the whole situation a new degree of freedom. This was the way in which you could add an extra degree of freedom to the carrier of the weak force, this weak intermediate boson, which first could only spin in two ways, but now adding this degree of freedom, now we can make a massive particle that can spin in three ways. This is the missing spin component. That was how Engler and Brout described symmetry breaking, and it also allows us now to understand how Young-Mills forces can be forces that deform a particle into a different particle. Because if there is a Higgs field present, the field also points in a certain direction, but now you can introduce a force between the Higgs field and the electron and neutrinos. And now you can demand that the force is different if the particles are parallel or if they are orthogonal. So the Higgs field orthogonal to the electron allows the electron to get a mass, but does not allow the neutrino to get a mass. Sometimes this particle is called a God particle. It is a particle that generates mass. It is not quite fair. We now know also neutrinos have a mass due to some other source. It wasn't God that gave the neutrino a mass. But as a physicist, I don't like the name God particle. God has little to do with it. It is just an ingredient of our theory. Now, this way, spontaneous symmetry breaking solved two problems. It solved the problem, how can a Young-Mills force be transmitted between particles that are somewhat or quite a bit different, and at the same time it explains how the force can become short range. And however, there is one very important thing I should add, however, there is something that this theory predicts that you might not have foreseen. And that is if you introduce a Higgs field that acts as a reference to distinguish electrons from neutrinos, that field itself must have dynamical properties. And as a consequence, also the length of this vector might vary a little bit. The vector might become a little bit shorter, it might become a little bit longer, and that implies there is another degree of freedom that had not yet been foreseen in the original theory. That is what Veldman and various others had missed in their earlier analysis, that also the length of this vector can vary. If you ignore all that, you are breaking the symmetry by hand in the equations. But if you use spontaneous symmetry breaking, you use an extra field that also can have a variable length. In the picture of the Mexican hat, we say that the particle that falls in the rim can generate this degree of freedom, but it will have another degree of freedom as well. It can oscillate in the radial direction here. Whether or not it can oscillate in that way depends on how stiff the Mexican hat is, how sharp is this rim of the hat. Depending on that, the energy needed to rotate in this direction will be different. And that energy corresponds to the mass of a new particle called Higgs particle. And this was the actual degree of freedom added to the theory. Without the Higgs particle, the theory would not work. And that was the new discovery. The only thing is that if you make this assumption, we do not know a priori what the energy of this extra motion is. How stiff is the rim of the Mexican hat? This is something that the theory doesn't predict, so we have to wait and see and try to observe this particle. So this is the new prediction, a new particle that has spin 0, it is electrically neutral, and it should be there to cure the diseases of the theory that didn't have these particles. The people who first realized that you can make a model along these lines were these three gentlemen. Salam had the very broad general idea but didn't have the details. Glasgow had the details except the Higgs particle. Weinberg put the whole thing together with the Higgs particle as well. And Weinberg was the first one to write down a model that has these features built in. So he said the electron and the neutrinos can make transitions due to Young-Mills fields. But if you analyze the observations very carefully, you find that they only make the transition if these particles rotate in a certain way. If you smash the neutrino in a certain direction, if it rotates to the left, it can make a transition to the electron. Same thing for this neutrino. If it rotates left, it can make a transition to the mu. If it rotates to the right, it cannot make such a transition. Right rotating neutrinos in those days had not yet been observed, so maybe they don't exist at all. When the particles rotate to the right, they don't have a neutrino counterpart. That was the essential observation that Weinberg made. And then he said the carriers of the weak force, there have to be 3 of them. There has to be a neutral component. This was new, had not yet been observed, but because left and right here are different, the photon itself cannot do the job. So there had to be yet another carrier of the weak force, a neutral component. And then they predicted this Higgs particle. It had to be somewhere with some mass. We don't know how heavy it is, but if you leave it out, the theory becomes inconsistent. So now Weinberg was a very wise person. He only wrote down his model for the leptons. As you saw in one of my first pictures, leptons are only part of these subatomic particles. The others are hadrons. In more modern terms, we know that the hadrons themselves are composites. They are built of quarks. So Weinberg could have written down his theory for quarks as well. But he was very wise not to include the quarks in his model. And the reason he said was that he did not understand the quarks. And that was important because if you look at the observations, there would have been a discrepancy, a disagreement with the observations if you tried to do this for quarks. So Weinberg realized this. He did not want to make a mistake, so he left the quarks out altogether and said, I don't know what the quarks are doing, but this is for the leptons. This was correct. This was the only thing he could do because it was something he did not know. In those days, it was thought only 3 species of quarks exist. There had been theories about a 4th species, but Weinberg did not know about that, and he didn't believe in it. And he didn't realize that the 4th quark would solve his problem. Now that it was known, now that it is known, we can also add the quarks to the same theory. Now the counting process works. At very high energies, very small distances, you can ignore the fact that the symmetry is spontaneously broken. In that case, you say there are 3 Young-Mills fields, but they only spin in 2 directions. There are actually 4 components to the Higgs field. In my previous picture, you could only see 2 of those, but actually they form a higher dimensional space, which is difficult to explain on the screen. Of these 4 scalar fields, 1 represents the length of the vector, which is the famous Higgs particle. The 3 others make the other particles massive. But at small distances, there are simply 4 of these particles, and there are 3 photon-like objects. Altogether, there are 10 degrees of freedom, 10 different ways in which a field or a particle can behave. So we say there are 10 species of particles, or equivalently, species of fields. At lower energies, at large distances, the spontaneous symmetry breaking becomes obvious. And in that case, you describe the same situation, but you say there are 3 massive particles which make the range of the weak force only very short. They must be able to spin in 3 directions. We use the word helicity to describe the spin degrees of freedom. 3 spin helicities. So there's 3 times 3 is 9 different species, different ways in which the Young-Mills particles can now rotate. Now, this Higgs particle gave 3 of its degrees of freedom away to the Young-Mills bosons. 1 degree of freedom was left, the neutral Higgs particles that we are still searching. 3 times 3 plus 1 is 10 degrees of freedom, and now the numbers match. So the theory didn't work previously because the numbers did not match properly. Now they do, and now the theory works just beautifully. This was the discovery. When the machine that we called LEP, Large Electron Positron Collider, was switched on, it was for one very important purpose. Previously, other machines had discovered this part of an important curve. This curve describes cross-sections of particles. What is a cross-section? When 2 particles collide, they sometimes collide and sometimes they go straight through as if nothing happens. If you measure how frequently do particles collide, what you're actually measuring is how big are they. If they're big, they collide easily. If they're very small, they have more difficulties colliding. So when you measure how frequently particles collide, you actually measure something that looks like the size of the particle, or more precisely, the cross-section. So regardless whether it's a real physical size of the particles or whether they go through each other as if nothing happens, we've learned to use the concept of cross-section to describe how often particles collide. And now you see cross-section depends on energy. I take 2 electrons, or electron and its antiparticle, E plus and E minus, and at a certain energy, certainly become much bigger. And they collide, and they collide very often here, and then they go down again. This peak is caused by the Z0 particle, the neutral component of the weak force. So this was a fantastic confirmation of the details of Weinberg's model, that there was a neutral component to the weak force, and we could measure it very precisely. LEP also enabled us to measure very precisely the charge component, but that is a different kind of plot. Anyway, after LEP was built, it observed these particles. It stopped right in the middle of this picture. The energies went to about 120 or so GeV. That was how LEP was designed. But later, people got very curious about how does the curve continue. And so LEP was reinforced. A stronger version was made that could go to much higher energies. Originally, in particular, the French members of CERN insisted that the machine should not go further than 200. So they designed the machine to stop at the value 200 and check whether there's any deviation from the theoretical curve. They found no deviation at all. The theoretical curve and the experimental observations match just perfectly here, as if absolutely nothing new is happening. However, if the Higgs particle exists, it should give another small peak in this curve corresponding to the Higgs particle. Where is the Higgs in this picture? It isn't there. So then LEP had to be shut down, but just before shutting it down, the people asked, how far can it go? Can we stretch the energy a little bit beyond 200? And yes, they went to 210 and found still no Higgs. And then there was a lot of discussion, should we run the machine another year to be able to extend the curve a few millimeters beyond this point? And well, it was decided to shut the machine down. We are not sure whether this was the right decision. We can't be sure, but maybe in the future we'll discover we made a big mistake. We should have run the machine a year longer to detect whether the Higgs might sit just beyond that point. We don't know. We still don't. This is the picture that you have today. This is a scientific picture that needs some explanation. We check today's observations, precision measurements, with the theory, the theoretical predictions. And when we check we express the result in a graph. It looks like this. The vertical line is the degree of match between theory and experiment. 0 means perfect matching. 2 means we are slightly off. 6 means we are rather badly off. There's a mismatch between theory and experiment. And horizontally we plot the mass of the Higgs in a logarithmic scale. So here it is 100 GeV, 200, 300, 400 until 1000. Now you see here that if you choose it about 600 or so, then the match is rather bad. It's over 6 units. It means there's something wrong in the comparison between theory and experiment. If you stay below 2, there's no serious problem between theory and experiment, which means that the Higgs mass could be up to about 400 without getting a serious discrepancy. The yellow region is already excluded by lab. So these are precision measurements different from the explicit check. So without the lab measurements, we didn't know whether the Higgs could be here as well. But now that is excluded. So the lab has excluded the Higgs slightly beyond the 100 GeV, but it could still sit at the right-hand side of this curve. Now, the strong force would require me to give a similar lengthy story about the strong force. I won't do that, there's no time for that anymore. But there's a very important distinction between strong force and electromagnetic and weak forces. Electromagnetic forces have force lines which spread out in a very familiar pattern. If you have electric charges and you separate them, the fields spread in this particular way. But if you do the same thing for quarks, you find that there's a strong force between the quarks. The field lines don't spread. This is now understood. Also, the strong force is a Young-Mills force. And so, but the equations are much more complicated and nonlinear, and that's why they behave very differently from this. So the strong force is a very different force. And this is now also going to be studied at the LHC. When we take two lead nuclei, which consist of lots of protons and neutrons, when they collide, it is expected that a new form of matter will be realized. The matter consists of the quarks and the Young-Mills particles, called gluons, and they combine here to form something totally different from what's inside the nuclei in the cells. This we call the quark-gluon plasma, and will be studied at great detail in the LHC. Then we also think about unification, but I should skip this picture because I really no time to discuss it. But this is the idea of further unity among the particles and the fields. My time is running fast, so I'm trying to skip some of these details. How does a machine work? How do we accelerate particles? If we take a charge difference between two electrodes, the electric fields in there will accelerate any charged particle. So a charged particle running through its electrodes will gain energy proportional to the voltage difference between those electrodes. If the voltage is 1 million volts, that's about the highest voltage you can reach without having discharges among the electrodes. With these voltages, the particles will generate 1 mega electron volt energy. We call the energy the particle gets if it goes through 1 volt, we call that electron volt. This would be a particle with 1 million electron volts. How do you get beyond that? Well, if you want to go beyond that, like 7 billion electron volts, or trillion electron volts, I should say, the energy now reached by the LHC, you can only get that by having particles run through electrodes very, very many times. There's a voltage difference here, and when the particle comes here, you switch the voltage between these two electrodes, and when the particle is here, your voltage difference is here, and so every time the particle goes through two sets of electrodes, it gains 1 million volts of energy. This way you can raise the energy to much higher values. But you want the particle to traverse various times, many times. And that's why you want the particles to go in circles. That's why you want the circular motion of the particles. You want to accelerate them to trillions of volts. And this is now what the LHC is doing. So to make them go in circles, you need a magnetic field, and that is, if the magnetic field lines go like this, the particles will bend around. So you need a large number of magnets to make them go full circle. Here you see one magnet being lowered in the LHC tunnel. That's quite an operation. This thing is 35 tons. You need strong cables. This is the geography of CERN. These are the older machines. CERN, the terrain of CERN is right here. So these accelerators are on the original CERN site. But now a bigger machine was built a number of years ago now called SPS. Is all underground, so you don't see this. And now the LHC is this very big circle. Things are not up to scale. The SPS is 300 meters in diameter, and this is some 10 kilometers in diameter. So this picture is not to scale. And various detectors are built on these sites. 4 major detectors called Atlas, ALICE, LHCb, and CMS. 4 different kinds of detectors. The idea is we want competition. We want 4 different groups to look at the same collisions with their own methods to see if they can compete and try to be the first to detect new phenomena. This is one of the main detectors to which also the Netherlands has contributed quite a bit, which is why I know this detector the best. To see how large it is, you have to realize there's someone standing here. So that shows you the dimension of the detector. Here it is still being built. It is not ready, but you see that there are gigantic coils here which are needed to generate other magnetic fields to detect the particles. Actually, after it is finished, it is much less spectacular because the whole thing is filled up to the rim with electronics. You can't see through it anymore. But the beam pipe goes right in the center, goes through, and the collision takes place right in the middle of the detector. Particles go in all directions and are being analyzed, and they go straight into the computer after analyzing them. This is another machine called ALICE, and this is the machine which is in particular designed to study what happens when the heavy lead ions meet and produce a quark-gluon plasma. The physicists working on this detector are particularly keen to study the quark-gluon plasma. A third machine that is looking very carefully at the muons that are produced in these collisions is called the compact muon solenoid, or CMS. And there's a third machine which looks at one type of quark, the so-called beauty quark, and so this is the so-called beauty generator, LHCb. This is a simulation of the event that would be generated by a Higgs particle. The Higgs particle only has a very short lifetime, so you don't actually see it decay. It decays instantly into some other particles, and those other particles then have to be detected by the electronics behind this. You see, it is tremendously complex. The computer has to analyze these data as fast as it can and as many times as it can. We want to have very large statistics. Millions of collisions take place every second. The computer selects hundreds of thousands of these in its memory and for later detailed analysis to figure out whether a Higgs has been formed or not. Now I briefly want to mention that there was an important accident happening in September a few years ago, September 19, 2008. It was a black page in the history of CERN. A big accident happened. Fortunately, no human casualties because there was nobody around, fortunately, because an explosion took place. One of these 35-ton magnets stood up and was displaced and went down again due to a gigantic explosion. What happened? What went wrong? To repair all the damage, which was considerable, took a couple of months. But the problem was, why did the accident happen, and how can we prevent that from happening? And to mitigate that, and to make sure that this accident doesn't happen again, took more than a year of detailed analysis and modifications in the design. What happened was, in one of the connectors that connect the superconducting cable of a magnet to a room temperature cable here, had to be soldered with a very special kind of solder, silver solder. And the resistance of the connection had to be very low. When I put a lamp on my bicycle and I make a connection and the resistance is less than 1 ohm, I would be very proud. I probably never achieved that when I solder a lamp in my bicycle or whatever. But this had to be nano ohms, 1 billion times better than a lamp on your bicycle. So if it is not a nano ohm, it will generate heat, and heat will turn a superconducting material into ordinary material. It will generate much more heat, and then the whole thing, there's such a high current in here that the connector will melt and evaporate. That's what happened. The entire connection melted and evaporated. Now you have to remember, there is enormous amount of energy inside this magnet, megajoules of energy. So much energy that if you interrupt the current just doesn't stop, the current continues. What happens is the same thing that happens in one of these fancy science fiction movies. You'll get a spark. The spark continues to carry the current even if there's no connection at all, but the spark will be over 1 meter or so wide, and it will start to jiggle, just like it does in the bad movies. So it jiggles, and then when the spark jiggled, it hit a liquid helium pipe. That is what it was not supposed to do that. The liquid helium, when it has a volume, only 1/1000th of the volume of vaporized helium, but it vaporized instantly, so the volume in that pipe increased by a factor 1,000 in a fraction of a second. That gave the explosion that put the magnet somewhere else. It damaged neighboring magnets. Some 30 or so magnets were being damaged and had to be either repaired or replaced. That was the major incident. So it took over a year, but during that year, all people could do is to redo all their calculations as accurately as they could. Consequently, it was also a beneficial event because it allowed people to be better prepared than any time before for the experiments. Here you see some of the statistics. I won't go through all of this. This is just to impress you with the large numbers. As a major fraction of the world's supply of helium goes into LHC, 130 tons of liquid helium. And then you see enormous amount of energy in all the magnets, tons of superconducting material to make the magnets work, and so on. With tremendous precision in the fields, you need also this high precision. In the meantime, there is the competition in the United States. There still is competition in the form of Fermilab. Their energy is considerably lower than the energy of the LHC, but still sizable, and they also try to find the Higgs particle. Seen from above, the LHC looks like this. Again, now it's 2 circles in which protons and antiprotons are moving, and they are made to collide at various spots, and they also try to identify the Higgs particle. This is a situation you had a couple of months ago. Today it's slightly different, I'll explain. Lab told us there's no Higgs below 114 GeV, according to the latest analysis. So the green spot means no Higgs there. LHC in the meantime has already told us there's no Higgs beyond 185 GeV. Maybe there's a very heavy one, but that would contradict some of the precision measurements. So we rather do not think about that. Then our measurements would have been wrong, but it's not totally excluded. Maybe some miscalculations have been made, and there's a very heavy Higgs way off the screen. Fermilab did a useful job here. It excluded the Higgs in this domain, but they are still analyzing their data today, even though the machine already has been shut down. The data are still being analyzed, and they are widening this region where no Higgs was found. But there still is a narrow region, which is white here. The Higgs could exist in this region. The reason why these different regions exist is there are different ways in which a Higgs particle can decay. If it decays into W plus W minus, it must be fairly heavy. In that case, it's rather easy to detect, and that's why we can exclude this domain. If it decays into B bar quarks, that's slightly easier. Fermilab has already excluded that decay in this domain. But if it decays into photons, that's the most difficult decay. But it has also been analyzed by Fermilab and by LHC, and they're both quite busy trying to narrow down this gap. Does the Higgs exist or not? That's the big question. So naturally we like to know, suppose that the Higgs is not found. By the way, I still don't have the latest data in. They're keeping it secret. It's not yet known whether today the Higgs has been found or not. When this lecture was planned, we didn't know whether the Higgs would already be found or not found. That's the title of this lecture. But we do not know it yet, so the game is still open. So we can ask, what if the Higgs is not detected? Well, then we have to look for alternative theories. The claim is, the machine builders assured us, the machine works so well that if the Higgs exists, we'll find it. If it doesn't exist, we'll be able to exclude its existence. So what if it is excluded? Then we have to modify the theory. Well, it could be that many Higgses exist. For instance, the up sector of the particles could be coupled to a different Higgs from the down sectors. Different particles might require different Higgs fields. If so, that would correspond to having very many Higgs particles. If you have many Higgs particles, each of which plays a different role in the game, then it will be, all of them will be much harder to detect. They'll spread just to disguise themselves, to make themselves more invisible. And that could be the situation. It could be that the Higgs is very heavy. Then some of our calculations aren't quite right. So we have to investigate why the calculations gave us the wrong results. That will require lots of work, but that is still quite possible. Strictly no Higgs would require a much more drastic reformulation of the theory. We would then be left with a great mystery. Why does our theory up to today work so well? And how come that in spite of the excellent agreement between observations and data, nevertheless exists in spite of the fact that the theory is wrong way inside? That would require to be explained, and we don't know that. We have to wait and see what LHC will give us. But I can certainly say there's no way we can lose here. Now, there's another thing that LHC will be interested in, and I think my time is running out, but I'll... so there's so-called notion of supersymmetry. There are two kinds of particles. I sometimes use the word boson to indicate particles where the spin is an integer number, either 0 or 1. Or I use the word fermions, which have either 1/2 or -1/2 as a spin. Now, bosons and fermions are fundamentally different particles, but according to some modern theories, you can put them all together into one superior theory called supersymmetry. Particles could exist that can spin both with integer and half-integer spin. These supersymmetry theories would be very valuable, and since spin is a property of space and time themselves, it means a modification of space-time. The first new modification of space-time since Einstein designed special and general relativity. Special and general relativity force us to look at space and time in a new way. This theory again would force us to look at space and time themselves in a new way, and therefore this would be a very important discovery if true. Unfortunately, our modern theories do not allow to combine any of the known bosonic particles with any of the known fermionic particles. So the known particles do not fit in such a scheme. But maybe new particles will be discovered which do. If they do, we hope that LHC will find this particle. But so far it has not. I should mention perhaps that, or in this plot here, this is one of the latest results of the exclusion. I won't go into details, but people are working very hard with the LHC data of today to see how well is supersymmetry faring. Not very well, because many enthusiasts of the symmetry propose that it should exist somewhere out here, but already the exclusion line is shifting more and more above and to the right of this picture, and that is problematic. Supersymmetry is not yet been seen by the LHC. We are at the same time studying many other things. LHC is comparable to a gigantic telescope. If an astronomer makes a big new telescope, he is not going to use it to look only at one star or one planet. They'll use a telescope for as many different things as possible. Same thing for the LHC. It's going to be used to study the quark-gluon plasma, to study supersymmetry, not only to study the Higgs. say dark matter is a new form of matter predicted by astrophysicists who noticed that there are gravitational fields between and inside galaxies that cannot be accommodated for by any of the known particles that we see that send light into our telescopes. So there is a form of matter that has not yet been identified. Maybe it has to be added to the standard model. Maybe LHC will find the first trace of that. And there are the more exotic possibilities, extra dimensions, black holes, you name it. Maybe LHC will make an unexpected discovery. Usually when you make a new machine to investigate a new area of the region of nature, you will make new discoveries. We will be very eager to be there when new discoveries are made. So far, LHC has not come with anything as spectacular as that, but we are only beginning observations. LHC is not yet running at the full design energy. They're still too afraid to switch on the magnets at full power because this accident could happen again. It has not yet been completely excluded. LHC will be taken out of service a year from now, and it will be out of service for more than a year to put the largest improvements there and assurances that no mishap of any sort can happen as it happened in 2008. So LHC can safely be turned on to work at full energy and as the highest possible luminosity. We want the numbers of particles that collide to be as large as possible, to analyze as many collisions as possible, to do statistics and to find a very weak signal in statistical data that could betray the existence of the Higgs particle and possibly as many other particles as are there to be found. So physicists will not rest until they investigated all possibilities of this machine. And that is where I would end my talk, and I would love to answer questions if they are there. Thank you.